this tutorial, we'll cover the questions on homework number 22. Let's start with finding the average rate of change from an equation. So if given a function equation and given an interval of which you are to find the rate of change, you simply enter this equation into your graphing calculator in the y equals button. So negative x squared plus 10x plus 33. So negative x squared plus 10x plus 33. Let's take a look. Did I write that right? Negative x squared plus 10x plus 33. Yes. So what we're going to do now is we're going to find the points that have x values of x value of 0 and an x value of 6. So for us, we do that by looking at the table, which is here in the blue feature. So second graph, and we can see our table and we can scan up and down. So I want the points for 0 and 6. So when I'm looking at my table here, I'm going to circle them for you. I'm looking for 0 and 6. So the 2 points that I want are 0, 33 and 657. 0, 33 and 657 are going to be what we use here. Actually, let me go back here. So 0, 33 and 657, those are our x and y values. And when we use our rate of change formula, right, which is delta y over delta x, when we use that formula, y2 minus y1 for x2 minus x1, then all we need to do is set up our fraction here and enter these values in the correct positions. So y2 is 57, that's the second y, and y1 is 33, and x2 is 6, and y1 is 0. So 57 minus 33 over 6 minus 0. So you can use your calculator to help you out here. 57 minus 33 over 6 minus 0. So 57 minus 33 over 6 minus 0. And we get our final answer, which is 4. So we can go back here and we could type our answer in, which is 4. So you do that each time. You enter this equation into your calculator. You look at the table to find the point for -1 and 5. All right, let's take a look at the second one, which is doing the same task, average rate of change, but comparing different functions. So it says here we're going to talk about function f, which is in the graph, function g, which is in a table, and function h, which is an equation. And it wants us to select the option that represents the ordering of the functions according to their average rates of change from -3 to -1, from least to greatest. So from -3 to -1. So for the function f, -3 is here, and I believe it was -3 to -1, okay. So -3 to -1 would be the points, -3, -8, and -1, 0. So the rate of change for this function is 8 over 2, which is 4. So the rate of change for function f is 4. I'm going to clear that out. I'm going to scroll this down a bit. Okay, here we go. The rate of change for function f was 4. The rate of change for function g is going to be 13 minus 31 over -1 minus -3. And the rate of change for function h, we would need to go get those points from a table by using our graphing calculator. All right, so let's see here. For function g, we're going to get here -18 over 2, which is -9. So we've got 4 and -9. So I'm going to erase my screen here so I can go grab this data point. From the function x squared plus 2x plus 4. X squared plus 2x plus 4. So I need to go here, clear out my function, x squared plus 2x plus 4. I'm going to go grab the points, which again were -3, so I need to arrow up, and -1. So let's see here. -3 and -1. So that's -3, 7, -1, 3. So my rate of change is 3 minus 7. Oops. 3 minus 7 over -1 minus -3, which is going to be -4 over 2, which is -2. -2. So going back to my questions, we had 4, we had -9, and we had -2. So it looks like the lowest is g of x, then it's h of x with -2, and then it's f of x with +4. So -9, -2, +4, that's the order from least to greatest, which is what they asked for. G of x, h of x, f of x. So I'm going to scroll down here, I'm going to choose that option. G of x, h of x, f of x, and submit my answer. So again, from the graph, you grab the points yourself. You're looking at the specific interval. From the table, you circle only the points that they're indicating. And for the equation, you have to put it into the calculator and find the points yourself. Now let's take a look at the next topic, which is interval comparison. Still average rate of change, but this one is on a single graph. And they're looking for you to find the greatest rate of change between each of these 2 points. So we're looking for the steepest slope, or we can do the math for each of these separate sections here. So for the first section, you'll notice here from 0 to 2, right, that's the point 0, 0 to the point 2, 5. So my rate of change is 5 minus 0 over 2 minus 0, which is 5 halves. My next one is from 2 to 11. So from point 2, let's use a different color this time, 2 to 11, so 2, 5, and 11, 12. So that would be 12 minus 5 over 11 minus 2, which would be 7/9. So this one is 7/9. And then we have 11 to 23, and then we have 23 to 31. So this third one here, 11 to 23 would be 11, 12. 23, 19, and we'd have 19 minus 12 over 23 minus 11, and that would be 7, and this would be 10 over 12, so this one is 7 over 12, and then our final one, I'll do that one in green, is 23, 19 to 31, 26. So let's see, 26 minus 19 over 31 minus 23, and let's see, 26 minus 19 and 31 minus 23 is 8, so 7/8. All right, so these are pretty easy to compare here because they're all 7s in the numerator. The higher the denominator, the smaller the item. But if you're not sure, you could also convert all of these into decimals to help you figure them out. Right, 5 divided by 2 is 2.5. 7 divided by 9 is less than 1, right? See how this is a fraction less than 1. This is a fraction less than 1. This is a fraction less than 1. This is the only one that's improper. So that has got to be the highest average rate of change. So you can convert them to decimals, or you could just understand that this is the highest value. All right, we're going to do something new here, adding and subtracting polynomials, also known as combining like terms. So here, because it says to add these items together, oh no, this one actually says subtract. So this one is a little bit tricky, so pay attention here. If you are subtracting you are actually going to distribute that subtraction sign to each of these values. So we're going to get 3x squared minus 10x minus 2. This one stays the same, or we keep it, right? And this one's going to change to combining or adding all of the opposite numbers. So the opposite number here would be negative 6x and negative 3, or subtract 6x, subtract 3. So you notice I've lined these up vertically instead of horizontally because I like to combine my like terms this way. There's nothing to combine here. Negative 10 take away 6 is negative 16, and negative 2 minus 3 is negative 5. So you're going to type that down here in your box, and in order to get an exponent, you can either press Shift 6 or you can use this delta keyboard. All right, you can use this delta keyboard here and you can get an exponent, or you can type Shift 6 yourself. So 3x squared minus 6x minus 5. Let's try this one more time. Okay, this time we have an addition sign in the middle, which means we are simply combining like terms. Negative 8x squared plus 5x plus 3, and then we're going to add 6x plus 6. So I like to add these vertically. Negative 8x squared plus 11x plus 9. So again, you can use the keyboard or you can type Shift 6 to get to that power position. Plus 11x plus 9. Clear my screen. Submit my response. Okay. The next topic for us here is moving into exponential functions. So in order to convert a table to an exponential function, you can either look for the pattern yourself, or you can use your regression capability on your TI-84. But an exponential function looks like this, where this value represents your initial value, also known as your y-intercept. In a table, you would find a y-intercept when the x value is 0, and the b value is your rate of growth or decay. Oops, rate of growth or decay. Now remember, this pattern might be constantly the same, but this is not called a constant rate of change. So with an exponential function, you are either multiplying or dividing, and we call dividing patterns multiplying by a fraction. So these are factors. So sometimes they call this the factor, right? The growth factor. So each time here I'm multiplying by 4. So my b value is going to be 4, and my a value is 3. So the equation I'm going to type is 3 parentheses 4 to the x power. So I'm going to type 3 parentheses 4 raised up to the x power. If you were not able to figure out the pattern on your own, or the pattern isn't perfect, that's when you would use a regression equation. So you should be able to compute these quite quickly. You shouldn't need to use a calculator, as long as you know that the format is initial value. For us, it's a 1. And then your rate of growth or decay, whatever your timesing pattern is here. If you're timesing by 2, then the pattern is 2. You can choose to leave an initial value of 1 invisible if you'd like. So 1 parentheses 2 to the x power. You can leave that the 1 invisible. So this would be given full credit, and the 1 being not there would also be given full credit. All right, the next one we're going to do is context, where if you're given a verbal story, you have to choose whether it is linear or exponential, right? Or in this case, linear. Which of the contexts below represents linear growth? Remember, linear growth is a constant rate of change. It's an addition or subtraction of the same exact amount, not a percent, not timesing by a fraction, but exactly the same amount each time. All right, an elevator descends at a rate of 26 feet. A coin collection appreciates at 3.3%. the amount of a certain medication decreases by 1/4, and Victoria puts $30 a month into a savings account. So there are two here that are linear, and that means that it changes the same amount each time. Those are not percentages, and those are not fractions. So this is linear, and so is this one. But the question was, which one was growth? The word descend means to go down. So for us, putting $30 into an account each month would be linear growth. A reminder to you that exponential patterns have fractions or percentages, right? Which of the contexts below could be modeled by an exponential function? Could not, sorry. Which of the contexts below could not be modeled by an exponential function? So this is appreciating by a percentage, that is exponential. This is decaying by a percentage, that is exponential. This one is growing by a percentage, that is exponential. Taxi charge is a flat fee of $1.50 and then $1.25 per mile. That is linear. So the answer to this question would be the fourth one. That's the only one that is not exponential. So that's the main idea with these questions. If they are linear, they have a constant adding or subtracting pattern. Not a percentage, not a fraction. So let's take a look here. Exponential models and linear models. All right, we're looking here at a chart, and I don't exactly know whether it's linear or exponential when I look at it. So what I might do here is kind of do some quick math with my calculator, and I'm going to do 432.13, and I'm going to subtract the number before it. So 432.13 minus 212.13. Let's see what I get. I get a difference of 210. Whoops. And then here I'm going to do 643.18 minus 432.18. And I get 211. These are very close. They're not exactly the same, but it's not that big of a difference. So 853.18 minus 643.18, I get 210. Okay, so it's constantly around a very similar amount here. So I'm going to go with linear. So I'm going to say a linear function would better model the data because as x increases by 1, the y values change additively, meaning we're pretty much adding a very similar amount each time. The common difference, right, a ratio is a multiplier, but the common difference of this function is approximately 210. Right, we had 210, 211, 210, so we're going to say it's approximately 210. All right, let's try one more. Looks here to be adding one, adding one, adding one, and then here I could say plus 6, and here I could say 27 minus 9 is plus 18, and then I could say 81 minus 27 would be plus 54, but you notice how significantly different these are. Significantly different. So it's probably not a linear model. So I'm going to try figuring out what this timesing pattern is, and if you don't know it, even though I think you do, you would take the second value and divide it by the first. That's how you find the pattern. Second value, subtract the first, or second value divided by the first. 9 divided by 3 is 3. 27 divided by 9 is 3. 81 divided by 27 is also 3. So this one is an exponential pattern because they change by multiplying. And that means that the common ratio is 3. All right, we're going to take a look here at our last concept, which is conversions. So conversion is a continuous multiplication problem. So it's asking us to convert 500 cubic feet into gallons. There's going to be a lot of math involved here. So you're definitely going to need a calculator. So I have 500 cubic feet, 500 feet cubed, and I want it to be in gallons. So I'm going to need to somehow get this fraction that has feet cubed in the numerator to turn into gallons in the numerator. So I kind of have to know a relationship between cubic feet and gallons. And I see one right here in my reference chart. So 1 cubic foot is equal to 7.481 gallons. So there's two ways you can write this comparison. You could write it like this, 1 cubic foot over 7.481 gallons. Or you could write it the reverse. 7.481 gallons is 1 cubic foot. So there are two ways you can write your fraction, and you need to decide which one of those fractions you want. Now, because I have feet cubed in my numerator, the only way for it to go away is to have feet cubed in the denominator. So that means I want feet cubed in the denominator and gallons in the numerator, which is this fraction here. So I'm going to take the fraction I already have and multiply it by this fraction that I got myself from the reference chart. So I'm going to take out my calculator. I'm going to multiply 500 times 7.481. And I get this number, 3,740.5. Now, because cubic feet is in the numerator and cubic feet is in the denominator, and 1 times 1 is 1, right? 1. That means I have 3,740.5 gallons. I can leave this off, and this has disappeared. So now I have my value written as gallons. 3740.5. 3740.5. Submit that here. Oh, what did I do wrong? Oh, round to the nearest whole number, Mrs. Henderson. Reading is fundamental. All right, let's try it again. This time, hopefully I read correctly. I have 680 kilometers, and I want to convert it into miles, rounded to the nearest whole number. So I have 680 kilometers. I want it to be miles. Let's see if we can do this in one step. Any conversions here from, yes. So you need to think about which way you want to write your timesing fraction. So which way do I want to write my timesing fraction? So I'm going to times this by some fraction, and that fraction has to have kilometers on the bottom, and it has to have miles on the top, because I want these kilometers to cancel out. So that means 1 mile and 1.609 kilometers. So 680 times 1, and then 1 times 1.609. That gives me this fraction here, and that means I have to divide. So on my calculator, I divide 680 divided by 1.609. I get a really long decimal. And I'm going to round to nearest whole number, which is 423. 423. This time I'm going to get it right. 423. Yes. This time we're going to turn ounces into cups. Ounces into cups. So right now I have 6 fluid ounces, and I want to have it in cups. So in order for that to happen, I have to have a comparison of cups and ounces, which I have here. And one cup equals 8 ounces. So I'm going to get 6 cups over 8, and 6 divided by 8 is 0.75. Ooh, it didn't ask me to round this time. Did not ask me to round. So I'm going to type that exactly as it is, 0.75. So I know this topic is new for you. But all you are practicing here is setting up from the reference table your item, 9,900 pints, and turning that into cups by multiplying by some fraction from your reference chart. So let's see, do we have pints and cups? Do right here. 1 pint equals 2 cups. So 9,900 times 2 will give us 19,800 cups. 19,800 cups. Let's see, do these get any harder? Nope, weeks into days, right? So I have 17 weeks. I want to times that by something that has weeks in the bottom and days in the top. I know that 1 week is 7 days, so this is 17 times 7, or 119. Let's see. Is the last one any more difficult? Days into weeks. Nope, no difficult. All right, that concludes homework number 22.